Hello and welcome to the final of our summer series on Lost in Science. This week, Chris will be talking about the so-called conflict between physics and evolutionary biology. Claire will be talking about how defrosting ice sheets might release pathogens that could be a danger to us all. And I will be talking about nematodes and how they are just everywhere.
Yes, it was the Lost in Science. My name is Chris, and as I said in the introduction, I am talking about this new theory that claims to, as they put it, reconcile physics and evolution. I realised I don't think I gave the name of the theory, did I?
No, you didn't. You're leaving us all hanging. What's the theory? What's the name of the theory?
It's called assembly theory.
Assembly theory.
Assembly
okay, and
theory.
that's not the theory of having to assemble in large groups to listen to speakers. No,
okay. It's not. It's not. But that would make a lot of sense, wouldn't it?
It would. It would.
No, it's about how things are put together. So look, it is, as I said, also the introduction. It's kind of got a physics basis, like it claims to be, a physics-related theory. The paper was published in the journal Nature, and the authors, one of the authors is a chemist. The lead authors, the lead investigator, is a chemist called Lee Cronin. But there is a theoretical physicist / astrobiologist who's the other kind of lead researcher, Sarah Walker.
Wow.
So yeah, the fact that it's claiming to be physics and it's got a physicist on the author list, I think it fits as my physicists not behaving badly, but veering wildly across the rest of science. So anyway, and as I said, they claim to be able to unite physics and evolution, which has led to a lot of evolutionary biologists saying, we have no problem with physics. Why are you talking about this?
What is your beef?
No one thought there was a problem. Some people thought there was a problem, but I'll get to that later in the story. But yeah, it's led to a bit of debate, and a particular debate, I guess, about how what the purpose of this theory is. Because this theory, when it says it unites physics and evolution, it's not just concentrating not just on the mechanisms of natural selection, Darwinian natural selection that we know and love, but also trying to push that further into the origin of life.
Right.
And so trying to get a physics / evolution / theory that will help explain the origin of life, as well as the evolution once it exists. Because the origin of life obviously is one of those big questions, those things that's still debated, and it's sort of like people with different theories about what exactly happened. And this is attempting to, I guess, fill in some of the mechanics of that. So this is called assembly theory. Now, as well as making grand claims about evolution, they do make some grand claims about what they're doing to physics as well. They like to state that physics, their theory basically considers any kind of object, whereas physics normally only looks at point particles, which a lot of physicists would take umbrage with that as well. So I think they're going to annoy both the physicists and the biologists in this one, because physics is normally quite happy with objects that aren't points.
Right. Yes.
There is physics of, everything. Like, I feel like I don't need to explain this, but physics of materials, like materials science and materials physics.
Anything sort of made up of something.
Yeah, planets and stars and things.
Okay. So when they say points,
atmospheres.
Okay.
But they have extended physics from not only dealing with points to doing with things that are not just points, which is good on them for thinking that they've discovered something new. But they've got this idea of this general notion of, I said, it's about assembly. And so they try to quantify, I suppose, a kind of a form of complexity of something, of an object, which is useful for the ideas of evolution, but based on the history of the object. This is a key thing. So the key element for anything that you might look at is something called the assembly index. And they define this as the minimum number of steps that it would take to construct this thing out of its fundamental building blocks. So other people have tried to look at this kind of notion of how complex an object is by looking at its composition, this sort of stuff. The unique thing about this one is looking at the history of the item, not just what it's made out of. So it's looking at what it actually takes to assemble it.
Right. Okay.
You don't sound impressed. But the idea is, by doing this, they allow for selection, a form of selection, because it's based on the history, it's based on all the steps that have come before it. And you can do things like, once you have, for instance, you've assembled one object, then you can build on that to make other things. And so the things that come after it are sort of determined by the thing that came before it.
Right.
It sounds obvious,
I mean, yeah, this is starting to sound a bit like a video game.
So I guess the other way of looking at things, you look at the universe, you look at, say, in fact, one is in the chemist. They focused on the chemistry. You look at like all the different chemicals that exist.
Yeah.
And yes, they could all come together randomly by atoms combining. However, with this kind of notion, you look at how they're actually put together, you limit the number of things that can be created because it's based on the history of the things that came before it. So you're not determining things just based on the chance of something coming together.
What could be.
Yeah, but how it can actually be built. And so when you get a sample of different, the other key thing, though, is when you get a sample of different kind of chemicals, you can look at how many of them there are. Because I suppose the way that selection works will be some kind of constructions will be more favoured than others. And so if you find more of one particular kind of complex chemical, then it indicates that it's perhaps been selected for, rather than just appearing randomly.
Right.
Okay.
Right.
So, this is all sounding fairly abstract, I know, but this is not the first paper they produced. In an earlier paper, they looked at how they could actually quantify this notion of an assembly index. Using mass spectroscopy, you can basically break down the constituents of chemicals, look what they're made out of, and so you can kind of estimate their this assembly index. So they tried this on a whole bunch of different substances, things, coal and that sort of stuff, bacteria, sediment from, I think, the San Francisco Bay Area or something like that. And they looked at what they got from this kind of calculated assembly index and whether compared to something was of biological origin or not. And they found that anything that had an assembly index of about 15 or above usually had an origin in life. As in, it was so complex that it required some sort of biological system to put it together. Incidentally, the most complex one they found, the ones they tested, was beer. But it's not a so they found that it was pretty good. They didn't get any false positives, they said, but you could get false negatives. So there were things that were very simple but still the product of life. And one of them was notably 10-year-old Ardbeg single malt Scotch whiskey. So that one came out with a fairly low assembly index, even though it is perhaps as complex as beer to produce, at least.
Wow.
So
okay. So there's some issues here.
There's some issues. So it's not a definite thing that's saying that basically they said they've got no false positives. So you find something with a high assembly index, that it means it must be constructed by life, some system with genetic memory or something like that to be able to assemble this complex thing. But if something had a low index, it could be another byproduct of life, but you just can't detect it using the system. So that is one of the things. There are and this is where some of the criticisms come into this, because there are other kind of hypothetical products of life that people have pointed out that this system would not be able to identify. So one of the key things in this assembly notion, for instance, was, like I said, the number of copies of something. So basically, if there's a lot of copies of this complex molecule, for instance, that's been produced by some sort of life form. What this theory does, I think, the positives for it is that it does kind of look at the idea of selection, takes it beyond natural selection as is typically understood. So, it can address this question of how you get complex molecules that are precursors to life could arise. And they test out their theory on, say, polymers, creating more complex polymers. A model of how that could work. But the other big benefit, and the key thing is, as I said, one of the authors, the physicist and thing, is also an astrobiologist. And this is useful for looking at, say, life elsewhere in the universe. So we can't guarantee that life and other planets are going to be like it is on Earth. So we've kind of, though, been looking so far for chemistry like we have on Earth, which is why we get things like, we see methane on Mars, and on Earth, methane is produced by life forms. We go, could it be produced by life forms? But we don't know that it's not produced by some other geological form.
Sure.
So this essentially, in theory, allows us to identify molecules of any kind on a planet and analyze them to work out whether they could have been produced by life rather than by natural causes. They're complex enough. It gives us a way of measuring that and quantifying that. So it is quite useful for that purpose. They also talk about how potentially this could go beyond biology. So we can look at how selection could, or the concept of selection could apply in the way technology is developed. And so, again, broadening this idea beyond the simple kind of squishy world of natural selection. So, look, I think it has potential. Like I said, it's not clear at the moment whether it is solving a genuine problem, and most evolutionary biologists do seem to be unimpressed. But I get the impression it's not trying to replace their work, it's trying to extend their work. But look, it does make some very grand claims. So, look, it will be interesting to see, whether it does, I guess, assemble into anything more long-lasting.
July 2023, the world experienced an unprecedented heat wave, and it set some new devastating records as the hottest month in history. So, data published by the United Nations and the European Union's top climate agencies, the World Meteorological Organization, and Copernicus, they show that the average temperature for the first 3 weeks of July is tracking significantly higher than the current record from 2019. And 21 of Earth's 30 hottest individual days on record, that's 21 out of 30 of any days, occurred in July. That is incredible and devastating. So, just to go to one of the climate scientists from Leipzig University, Carsten Houston, estimating July finished a 0.2 degrees Celsius warmer than the 2019 record. So making it not only the warmest month on record, but potentially in thousands of years. And all this happening before El Nino, the weather system, climate system, I should say, it has even kicked in yet. So according to climate scientists, according to many people, it's a very worrying situation because, El Nino is a major climate driver and brings with it warmer than normal global average temperatures. It's not the same everywhere around the world, but in general, warmer than average. So we're looking at a sweltering northern hemisphere, caused by climate change, followed by what is being reported by researchers as now an extended hot period across the globe.
Yeah, and it's obviously this is like a heat wave conditions at the moment, and it's not saying that every July is necessarily going to be this hot going forward. But like you're saying, the fact that this has occurred before El Nino has gotten underway doesn't bode well for the coming year, at least, does it?
No, it really doesn't. And, amid rising temperatures and, like we talked about, the catastrophic wildfires and the heat wave, the sea levels, there's another potential ecological disaster that, I'm sure we don't want to think about, but it's always good to, you need to talk about this stuff. And that is the idea that ancient bacteria could be returned to ecosystems that have been under permafrost once that permafrost thaws. Yeah, because for centuries the Arctic permafrost, it's preserved microscopic organisms in a state of suspended animation and locked away from the world. But, as the permafrost or, frozen ground begins to melt, ancient bacteria are released into the environment.
So this like mammoths being, defrosted and come back, or dare I say Captain America perhaps being put on ice and coming back.
Yeah, and there's been some recent research. Now, this isn't thawed permafrost, but this is taking taking a piece of ice that had a roundworm in it, so a nematode. Scientists thawed that nematode, that roundworm, and have actually brought it back to life from an ice sample from 46,000 years ago.
Oh, so that's more than just a bacteria. That's like a multi-celled organism.
Yeah, that's a nematode, which, if regular listeners will remember, Stu, you had a story on nematodes very recently.
Yeah, it's an animal. It's well beyond bacteria level.
Yeah, yeah. So if nematodes can come back, then bacteria probably. It's a lot easier for a single-celled organism, I imagine. Now, there are many scientists worried about the implications here, and as we said in the intro, there are many science fiction stories out there that have, made their case speculating on what would happen from, with the release of different ancient bacteria, nematodes, mammoths, whatever you have, what would happen in terms of human health and ecology. Especially as these bacteria, they date back millions of years. So most immune systems, an adaptive immune system these days, won't be ready for to be able to recognize and fight some of these potentially pathogenic bacteria. So their reintroduction into our world and our ecosystems and, potentially our bodies, it poses danger. And up until now, that's been quite difficult to quantify. But there has been a new global study, and it's from the European Commission Joint Research Centres and Flinders University here in Australia, and it was published this week. And the paper's got a great name. It's called Time Travelling Pathogens and Their Risk to Ecological Communities.
Great Scott.
That's great, isn't it? Oh dear.
So can they go backwards in time as well as forwards in time? Like, what are their capabilities here?
It doesn't actually specify in the paper whether they are forwards and backwards time traveling pathogens, but I'll leave that one up to you. It's in an open access journal, PLOS Computational Biology, and here they calculate the ecological risks posed by the ancient microbes. So one thing to note about this study is that all of this was done on computer by using computer modeling. So the researchers constructed simulated experiments where they put in place ancient pathogens from the past into a simulated world ecosystem and modeled how these simulated ancient pathogens could invade communities of bacteria-like hosts that are living in the present. They then compared the effects of these sort of invading pathogens on host bacteria in communities where there was no invasion. So they did it against a computer modeled control as well. And what they found in their simulation was that the ancient invading pathogens could often survive and evolve in the modern world. So in about 3% of cases, the pathogens became dominant in a new environment. So overall, from their modelling, around 1% of the invaders were very unpredictable. And in this unpredictability, they found that around 30% of species in that environment died out. While interestingly, others increased diversity by 12%. So it's interesting to sort of see how they've sort of been able to simulate this. Now, you might think that 1% of released pathogens might seem small, but given the sheer amount of ancient microbes that could be released into the environment, the researchers say these outbreaks represent a substantial danger. Now, they point to an actual risk deriving from the rare events where pathogens, currently trapped in the permafrost and ice produce these ecological impacts. And, in the worst case, the invasion of a single ancient pathogen could reduce the size of its host community by about 30% when compared to our non-invasive controls. Now, like a lot of climate news from this month, this isn't really that great, but the researchers reiterate that, as a society, we do need to understand the potential risk posed by these ancient microbes so we can prepare for any unintended consequences of their release into the modern world. So, unfortunately, it's no longer science fiction, but there is really a risk that we need to be prepared to defend.
Across Australia on the Community Radio Network, you're listening to Lost in Science. There's an often cited figure that puts the number of beetle species highest among animals, but just recently I've been reading, I think there might be a challenger for the crown: nematodes. Nematodes are also known as roundworms. Sometimes they're also called eelworms, especially if they're parasitic on plants. But they're not really closely related to worms or earthworms or other segmented worms, and they're much, much smaller. They're microscopic. But nematodes are found in ecosystems from the life aquatic in both freshwater and marine environments, and even down in deep sea trenches, and ubiquitous in terrestrial environments from alpine areas to deserts, and they're usually living in the soil. If you want to get an idea of the numbers of nematodes in the world, there are about 60 billion nematodes for every human being on Earth. That's a lot.
60 billion?
Yeah.
You can have some of mine if you want, Stu.
Thanks.
I don't need 60 billion.
Estimates of the number of species range from a very conservative 25,000 to probably a more realistic figure of around 1 million species of nematodes. It's just very, very hard to classify them. So there's 256 recognized families of nematodes, and there's over 2,000 accepted genera. They're so numerous that a pioneering nematologist by the name of Nathan Cobb said, if all matter except nematodes was removed, the Earth would still be recognizable due to a film of nematodes where every surface was. So many species are parasitic or pathogenic of other species of plant and animal, and more than 30 can affect humans, but that is a tiny amount compared to the sheer number of species that exist. And mostly they cause very few problems for humans or for domesticated animal and plant species. And in fact, some have been harnessed to help us out, being used as beneficial organisms in crop production and greenhouses to prey on other pests. So one species which is widely used for this purpose is called Steinernema carpocapsae, which is classified as an entomopathogenic nematode. It can be used as used to target pest insects of various species. So this nematode can detect carbon dioxide, and that is how it finds its prey, by finding its way into their bodies through their spiracles, which are the holes through which insects breathe.
Oh, right.
And the nematodes get into the spiracles.
Oh, gosh.
And get in there that way. But it doesn't work alone. It has developed a symbiotic relationship with a bacteria, which it carries into its host and releases along with a cocktail of other proteins. So the combination of pathogenic bacteria and enzymes produced by the nematode that break down the host's immune responses kill off the host in a matter of days.
Whoa.
Leaving behind a food source where the nematodes can feed and breed before they eat their way out to go in search of their next victim. Now, this might sound perfectly reasonable if a little ghoulish nematodes attack insects crawling around in the soil and eat them, and Hakuna Matata, it's the circle of life. But
that's not what Hakuna Matata means.
Yeah, sure it does. That's what that was the message I got from the Lion King. Did I misinterpret? But Steinonema carpocapsae doesn't just attack soil-dwelling prey, and this is kind of where it gets weird. It also attacks insects above the ground and even feeds on flying insects. As a generalist parasite, it's also known as an ambush forager. It can stand up on its tail and wait for passing insects to attach to, and they can even jump up into the air. Now, you would think you would have to be a pretty good jumper to catch onto flying insects, and a lot of research has focused on their jumping ability. The distances they can jump is quite astounding compared to their body size and all that sort of thing. But they also have another secret weapon, electricity. No, they don't shoot bolts of lightning at their prey. They take advantage of static electricity that builds up in insect bodies when they are in motion. So crawling around in plant litter on the ground and flying through the air, the insects build up a static charge just as they're moving around. So in research presented at the March meeting of the American Physical Society, some scientists used dead insects to test the hypothesis that static charges were helping the nematodes hit their target. They suspended non-charged insects above hungry nematodes and observed how many could hit the target. And they noted that basically only the ones who jumped directly at the insect were able to hit it, which is not really a surprise. That's pretty predictable sort of outcome. But when they tested a statically charged example, they found that even nematodes that jumped in the wrong direction found their target thanks to the static electricity. So they basically just jumped up in the air, and the static charge made them cling to this insect decoy, which is pretty amazing, and obviously a huge advantage for the little nematodes who just want to get in there and have their lunch, which is all fair enough for them. But I guess, if you're any other kind of insect trying to avoid being preyed upon by nematodes and you want to increase your survival rate, they have to just figure out how to lose their electric charge. And I think they wouldn't just be happier, they would be ecstatic.
Oh.
And that is all we have time for this week on Lost in Science. Thank you for joining us in Getting Lost. If you have any questions or suggestions for the team, get in touch with us by email. We are lostinsci@gmail.com. You can send cheap tweets to us at lostinscience1 on Twitter, or you can find us on the ubiquitous Facebook. Lost in Science is recorded at the studios of 3CR in Melbourne on the land of the Kulin Nation and is broadcast across Australia on the Community Radio Network with the assistance of the Community Broadcasting Foundation. You can find a podcast version of the show on 3cr.org.au, or you can tune in the way you did this week when we return in our usual time slot to get Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.